Welcome to Chapter 2, Structure of Atom. In this video, we'll journey through the fascinating history of how scientists uncovered the mysteries of the atom. From early theories to groundbreaking experiments, we'll explore how our understanding of atomic structure evolved over time. We'll start with Dalton's atomic theory, move through the discovery of subatomic particles, and examine the major atomic models that shaped modern chemistry. By the end, you'll have a clear picture of how atoms are structured and why these discoveries matter. Let's begin our exploration into the building blocks of matter. The early 19th century, John Dalton proposed a revolutionary idea. All matter is made up of tiny indivisible particles called atoms. Dalton's atomic theory laid the foundation for modern chemistry. He suggested that atoms of the same element are identical in mass and properties, while atoms of different elements differ. According to Dalton, compounds form when atoms combine in simple whole number ratios, and chemical reactions involve the rearrangement of these atoms. Although Dalton's theory was groundbreaking, it couldn't explain the internal structure of atoms or the existence of isotopes. Still, it marked a major step forward in our understanding of matter. While Dalton's atomic theory explained many chemical phenomena, it had its limitations. For instance, it couldn't account for the internal structure of atoms or the discovery of isotopes, atoms of the same element with different masses. As science advanced, new experiments revealed that atoms were not truly indivisible. Instead, they contained even smaller particles, leading to a deeper understanding of atomic structure. These discoveries set the stage for the next wave of scientific breakthroughs as researchers began to uncover the existence of subatomic particles within the atom. Late 19th and early 20th centuries saw a series of remarkable discoveries that changed our view of the atom forever. Scientists found that atoms were not indivisible but made up of even smaller particles, electrons, protons, and neutrons. Each of these subatomic particles has unique properties and plays a crucial role in the structure and behavior of atoms. Let's explore how each of these particles was discovered, starting with the electron, the first subatomic particle to be identified. Discovery of the electron began with experiments using cathode ray tubes. Scientists observed that when an electric current passed through a gas at low pressure, mysterious rays traveled from the cathode negative electrode to the anode positive electrode. These rays, known as cathode rays, were found to travel in straight lines and could be deflected by electric and magnetic fields. This behavior suggested that the rays consisted of negatively charged particles. These experiments laid the groundwork for identifying the electron as a fundamental component of the atom. 1897, J.J. Thomson conducted a series of experiments with cathode rays and made a groundbreaking discovery. He measured the charge-to-mass ratio (EM) of the particles in the rays and found it to be 1.7588 times 1011 C/kg. This value was much higher than that of any known ion, indicating that these particles were much lighter than atoms. Thomson concluded that these negatively charged particles, later named electrons, were universal components of all atoms. His work fundamentally changed our understanding of atomic structure. For the discovery of the electron, scientists wanted to determine its actual charge. This was accomplished by Robert Millikan through his famous oil drop experiment. By observing tiny oil droplets suspended between two charged plates, Millikan was able to measure the smallest possible unit of electric charge. He found that the charge of a single electron is 1.602 times 10 coulombs. This precise measurement helped confirm the existence of the electron and provided a deeper understanding of atomic structure. Studying discharge tubes, scientists noticed rays traveling in the opposite direction to cathode rays. These were called canal rays or anode rays, discovered by Goldstein. The particles in these rays were positively charged and much heavier than electrons. The lightest of these positive particles, found in hydrogen, was named the proton. Protons have a mass of 1.6726 times 10 to kg and a charge equal in magnitude but opposite in sign to that of the electron. The discovery of the proton added another layer to our understanding of atomic structure. Protons are fundamental particles found in the nucleus of every atom. They carry a positive charge of plus 1602 times 10 coulombs, exactly equal and opposite to the charge of an electron. Protons are much heavier than electrons, and their presence determines the atomic number of an element. This means that the number of protons in an atom's nucleus defines which element it is. The discovery of protons helped explain why atoms of different elements have different properties. Final major subatomic particle to be discovered was the neutron. In 1932, James Chadwick bombarded beryllium with alpha particles and observed a new type of radiation. This radiation was highly penetrating and carried no electric charge, leading Chadwick to conclude that it consisted of neutral particles, neutrons. Neutrons have a mass nearly equal to that of protons but carry no charge. Their discovery explained the existence of isotopes and completed the basic picture of atomic structure. Neutrons play a crucial role in the stability of atomic nuclei. Without neutrons, the positively charged protons in the nucleus would repel each other, making the nucleus unstable. Neutrons act as a kind of glue that holds the nucleus together. They also explain why atoms of the same element can have different masses. These are called isotopes. The discovery of neutrons was essential for understanding nuclear reactions and the structure of atoms. Summarize: atoms are made up of three main subatomic particles: electrons, protons, and neutrons. Electrons are negatively charged and found outside the nucleus. Protons are positively charged and, along with neutrons, are located in the nucleus. Each particle has unique properties that contribute to the overall structure and behavior of atoms. Understanding these particles is key to grasping the basics of chemistry and atomic theory. the discovery of subatomic particles, scientists began to propose new models to explain how these particles are arranged within the atom. Each model attempted to address the limitations of previous theories and incorporate the latest experimental findings. Let's take a closer look at the major atomic models that shaped our understanding of atomic structure, starting with Thomson's plum pudding model. A.J. Thomson's plum pudding model imagined the atom as a positively charged sphere with negatively charged electrons embedded throughout, like plums in a pudding. This model was an attempt to explain how electrons and positive charge could coexist within the atom. While it was a creative idea, the plum pudding model couldn't explain certain experimental results, such as the scattering of alpha particles. Nevertheless, it was an important step in the development of atomic theory. Despite its initial appeal, the plum pudding model faced significant challenges. It couldn't explain the results of alpha particle scattering experiments, which showed that most of the atom is empty space and that there is a dense positively charged center. The model also failed to describe how electrons are arranged or why atoms are stable. These shortcomings led scientists to search for a better explanation of atomic structure, paving the way for new models. Ernest Rutherford proposed a new model of the atom based on his famous alpha particle scattering experiment. He bombarded thin metal foil with alpha particles and observed that most passed through, but some were deflected at large angles. This led Rutherford to conclude that atoms have a small, dense, positively charged nucleus at the center, with electrons orbiting around it. The nuclear model explained the results of the scattering experiment and marked a major advance in atomic theory. Rutherford's experiment, alpha particles were directed at a thin sheet of gold foil. Most particles passed straight through, but a few were deflected at large angles and some even bounced back. This surprising result showed that the atom is mostly empty space, with a tiny dense nucleus containing most of the atom's mass. The experiment provided strong evidence against the plum pudding model and supported the nuclear model of the atom. Rutherford's nuclear model introduced several key features. The atom consists of a tiny dense nucleus containing protons and neutrons, surrounded by electrons in orbit. Most of the atom's volume is empty space. The positive charge of the nucleus attracts the negatively charged electrons, keeping them in orbit. This model explained many experimental observations and laid the groundwork for future developments in atomic theory. Despite its success, the nuclear model had its own limitations. According to classical physics, electrons orbiting the nucleus should lose energy and spiral into the nucleus, causing the atom to collapse. However, atoms are stable in reality. The model also couldn't explain the arrangement of electrons or the existence of atomic spectra. These issues prompted scientists to search for new theories that could address these shortcomings. Solve the problems of the nuclear model, scientists turned to quantum theory. Quantum mechanics introduced new ideas about how electrons behave in atoms. Instead of moving in fixed orbits, electrons exist in regions of probability called orbitals. This new approach explained atomic stability and the unique spectra of different elements. The quantum model represents the most accurate description of atomic structure we have today. The quantum model, electrons are not confined to fixed paths around the nucleus. Instead, they occupy regions of space called orbitals, where the probability of finding an electron is highest. Each orbital has a specific shape and energy level. This concept helps explain the chemical behavior of elements and the patterns seen in the periodic table. The idea of orbitals is central to modern chemistry and atomic theory. Electrons in atoms occupy specific energy levels, or shells, around the nucleus. Each energy level can hold a certain number of electrons. When electrons absorb energy, they can move to higher energy levels, and when they release energy, they fall back to lower levels. This movement of electrons between energy levels explains the emission and absorption spectra of elements. Understanding energy levels is key to explaining many chemical and physical properties. When atoms are energized, their electrons jump to higher energy levels. As the electrons return to lower levels, they emit light of specific wavelengths, creating a unique spectrum for each element. These atomic spectra are like fingerprints, allowing scientists to identify elements in stars and other distant objects. The study of atomic spectra provided crucial evidence for the quantum model of the atom. Niels Bohr proposed a new model of the atom to explain atomic spectra. In Bohr's model, electrons move in fixed orbits around the nucleus, each with a specific energy. Electrons can jump between orbits by absorbing or emitting energy. This model successfully explained the spectra of hydrogen but couldn't account for more complex atoms. Still, Bohr's model was a major step toward the modern quantum model. While Bohr's model explained the spectra of hydrogen, it couldn't accurately describe atoms with more than one electron. It also didn't account for the wave-like behavior of electrons or the complexities of electron interactions. These limitations led to the development of quantum mechanics, which provides a more complete and accurate picture of atomic structure. Quantum mechanical model describes electrons as existing in orbitals, with their positions and energies described by probability rather than certainty. This model incorporates both the particle and wave nature of electrons, offering a comprehensive explanation of atomic behavior. It successfully explains the structure of all elements and their chemical properties, making it the foundation of modern chemistry. Key idea in quantum mechanics is Heisenberg's uncertainty principle. It states that it's impossible to know both the exact position and momentum of an electron at the same time. This principle means we can only talk about the probability of finding an electron in a certain region, not its exact path. The uncertainty principle is fundamental to our understanding of atomic and subatomic particles. Erwin Schrödinger developed a mathematical equation to describe the behavior of electrons in atoms. His wave equation predicts the probability of finding an electron in a particular region around the nucleus. This approach forms the basis of the quantum mechanical model and helps explain the shapes and energies of atomic orbitals. Schrödinger's work was a major milestone in the development of modern atomic theory. Every atom is defined by its atomic number, which is the number of protons in its nucleus. The mass number is the total number of protons and neutrons. These two numbers help identify elements and their isotopes. For example, carbon has an atomic number of 6 and a common mass number of 12. Understanding these numbers is essential for studying chemical reactions and the periodic table. Isotopes are atoms of the same element that have the same number of protons but different numbers of neutrons. This means they have different mass numbers but identical chemical properties. For example, carbon-12 and carbon-14 are both isotopes of carbon. Isotopes play important roles in science, from dating ancient artifacts to medical imaging. Besides isotopes, there are other related concepts: isobars and isotones. Isobars are atoms with the same mass number but different atomic numbers, meaning they have different numbers of protons and neutrons. Isotones are atoms with the same number of neutrons but different numbers of protons. These concepts help scientists classify and understand the diversity of atomic nuclei. Atomic mass is the mass of a single atom, usually measured in atomic mass units AMU. It's determined by the combined mass of protons and neutrons in the nucleus, since electrons contribute very little to the total mass. Scientists use instruments called mass spectrometers to measure atomic masses with great precision. Accurate atomic masses are essential for chemical calculations and understanding the properties of elements. Most elements exist as mixtures of isotopes, so their atomic mass is an average based on the relative abundance of each isotope. The average atomic mass is calculated by multiplying the mass of each isotope by its natural abundance and adding the results. This value is what you see on the periodic table and is used in chemical calculations. Mole is a fundamental unit in chemistry, representing a specific number of particles, Avogadro's number, which is 6.022 times 1023. This concept allows chemists to count atoms and molecules by weighing them. The mole concept is essential for understanding chemical reactions, stoichiometry, and the relationships between mass and number of particles. Mole concept is used in a wide range of chemical calculations. It helps chemists determine how much of each substance is needed or produced in a reaction. By using Avogadro's number, scientists can relate the mass of a substance to the number of atoms or molecules it contains. This makes the mole concept a powerful tool in both laboratory and industrial chemistry. The law of constant composition states that a given compound always contains the same elements in the same proportion by mass. This law supports Dalton's atomic theory and is fundamental to chemical analysis. It explains why water is always H2O with 2 hydrogen atoms for every oxygen atom, regardless of the source. The law of multiple proportions states that when two elements form more than one compound, the masses of one element that combine with a fixed mass of the other are in simple whole number ratios. This law further supports the idea that atoms combine in specific ways to form compounds, as Dalton suggested. The law of conservation of mass states that mass is neither created nor destroyed in a chemical reaction. This means the total mass of reactants equals the total mass of products. This law is a cornerstone of chemistry and supports the idea that atoms are simply rearranged during reactions, not created or destroyed. Nucleus is the tiny, dense center of the atom, containing protons and neutrons. It accounts for nearly all the atom's mass but occupies only a tiny fraction of its volume. The arrangement of protons and neutrons in the nucleus determines the stability and properties of the atom. Understanding the nucleus is essential for studying radioactivity and nuclear reactions. The nucleus is held together by the strong nuclear force, which is much stronger than the electrical repulsion between protons. This force acts only over very short distances and is responsible for the stability of atomic nuclei. Without the strong nuclear force, atoms would not exist as we know them. Some atomic nuclei are unstable and spontaneously break down, emitting radiation in the process. This phenomenon is called radioactivity. Radioactive decay changes the number of protons or neutrons in the nucleus, transforming the atom into a different element or isotope. Radioactivity has important applications in medicine, energy, and scientific research. There are several types of radioactive decay, including alpha, beta, and gamma decay. Alpha decay releases a helium nucleus, beta decay involves the conversion of a neutron to a proton or vice versa, and gamma decay emits high-energy photons. Each type of decay changes the nucleus in a specific way and has different effects on the atom. Radioactivity has many practical uses. In medicine, radioactive isotopes are used for imaging and cancer treatment. In energy, nuclear reactors harness the energy from radioactive decay to generate electricity. Radioactivity is also used in scientific research, archaeology, and industry. Its discovery has had a profound impact on modern science and technology. We've covered the historical development of atomic theory, the discovery of subatomic particles, and the evolution of atomic models. We explored the quantum mechanical model, the structure of the nucleus, and the laws that govern chemical reactions. Understanding atomic structure is fundamental to all of chemistry and helps explain the properties of matter. Let's recap the key points before we conclude. This chapter we traced the journey from Dalton's atomic theory to the modern quantum mechanical model. We learned how experiments revealed the existence of electrons, protons, and neutrons, and how atomic models evolved to explain new discoveries. The structure of the atom is a cornerstone of science, shaping our understanding of chemistry, physics, and the universe itself. Keep these concepts in mind as you continue your studies in science.